All right. So I hope that you guys are already there. So may we continue now?
Yes, sir.
Baka nag-CR pa yung iba. All right. So we'll wait 1 more minute. Okay. Just 1 minute for the others. So I guess they are not there yet. All right. So I hope that you guys are already there. So do you guys have a question regarding with this one inverse of relation using a diagram? Diagram. Just a graph. Okay, not
What?
diagram. All right. So if there are no questions, then this is now your seat break number 4. So the relation are on the set 1, 2, 3, 4, 5, defined by the rule x, y is an element of R. Okay. So in here you only need to find the original set ordered pair and then inverse that ordered pair or that relation. Okay. So just a two-step process. Okay. So we have 3 numbers for this one: A, B, and C. All right. So any questions so far regarding with your seat break number 4?
Wala po.
All right. So again, you can do this one using Microsoft Word or handwritten. All right. So here's the another relation which is called composition. So in here you need 2 lists of relation or 2 sets. Okay. So we have here the R2 or R1 is the relation from X to Z defined by this formula. So for R2, if we have this format XY or XZ as your element of your R1 and YW and ZW or ZW for the R2, then you should have XW for your composition of relation. So in here, you're actually going to form a new relation. Okay. So two relation, which is you're going to compare the R2 or R1, and then you're going to form another relation, or let's say R3 or the R2 or R1, wherein we have this XW. All right, so as you can see right here, we have 2 relations or 2 sets of relations. We have R1 and then R2, and then they have their own corresponding sets or elements. And here's the solution. So the question here is R2 O R1. What is R2 O R1? So just apply this formula, then you will get this answer. So as you can see right here, if we have 1, 2, and then 2U, then you should have 1U. So as you can see, this one is similar with the implication, or what is that one? Transitive. Okay, this one is super similar with the transitive. Okay, it's just that it is coming from another set, not within that set, right? So in here we have 1, 2, and then 2U. So we should have 1U. Another one here is 1, 6, and then 60. Then we should have 1P. And then 2, 4, and then 4S. Then you should have 2S. And then 3, 4, and then 4S. Then you should have 3S. And then 3, 4, and then 40. Then you should have 3P. And then 3, 6, and then 60. You should have 3P. Oops. Yeah, which is already in here. And 3, 8, and then 8U. You should have 3. All right, so if ever there is a repeated ordered pair, so just remove that one since this one is in a set. So we don't need a repeated ordered pairs when it comes to sets. So all of them should be distinct ordered pair or distinct elements. So did you guys get this one so far? Composition of relation.
Yes, sir.
All right. So just be wary on the arrangement of the R2O R1. So R2O R1 is different with R1O R2. Okay. So whichever is on the last one, that should be your first element. Whatever is your first, say R2 here, then that one should be the second element. Okay. So you're going to compare this one from R1 to R2. All right. So we have here again your secret number 5. So we have two relations, and then here's the question: R1O R2, and then R2O R1. All right. So R2 R1 is similar with this example, and then R1O R2 is just the opposite. All right. So are we clear so far regarding with your secret number 5?
Yes, sir.
Clear po.
Yes, sir.
Yes, sir.
Now we have here the equivalence relation. Okay. So before we have the partial order, but in here we have the equivalence relation. Sorry, it's not equivalence order, but it's equivalence relation. So it's ER, not EO. So we have the PO for the partial order, and then we have the ER for the equivalence relation. So again, just like I mentioned a while ago, so we should have RST. So RST stands for reflexive, symmetric, and then transitive. Okay, so we have this example wherein if you're going to verify this relation as equivalence relation, so check one by one. So we have 1, 2, 3, 4, and then 5 up to 6. Yeah, 6 elements. So from there, you should have 1, 1, you should have 2, 2, should have 3, 3, 4, 4, 5, 5, 5, 5, and then 6, 6. So there you go. So reflexive is checked. But how about symmetric? So let's see. So in here we have 1, 3, then we should have 3, 1, which is 1. We have 1, 5, we should have 5, 1, which is this 1. And then 3, 3, no problem, 3, 5. So if we have 3, 5, we should have 5, 3, which is this 1. And then 2, 6, then we should have 6, 2. And yeah, so no more. So as you can see, this one is also symmetric. So check. And then for transitive, so this one is the longest process that you need to check. So if you have 1, 1, and 1, 3, then you should have 1, 3. 1, 1, and 1, 5, you should have 1, 5. What else? No more. So let's move to the next one. So 1, 3, and then 3, 3. So you should have 3, 3. So yeah, basically you just need to check all of those. So I will not check this one by one anymore since we don't have enough time anymore. So I will leave the verification part onto you guys. So I want you guys to verify this one, whether this one is really transitive or not. So if ever that this one is a transitive relation, then you could say that this relation is an equivalence relation. But if this one is not transitive, there is one ordered pair that is not meeting the requirements of transitive, then this one is not an equivalence relation. All right. So are we clear so far regarding with equivalence relation? No, guys? Are you guys still analyzing this one?
Yes, sir.
Yes, sir.
All right. So mamaya nyo just verify this one on the transitive part once we're done with our discussion. Okay. So we cannot stay here for around 2 or 3 more minutes since we still have 21 slides. Right? Just remember, okay, so I'm sorry. So this one actually has a solution. Okay. So this example has a solution. So yes, it's reflexive, yes, it's symmetric, and at the same time, it's also transitive. Okay. So thus making this example an equivalence relation. All right. So in here, it's the step-by-step verification or validation. All right. So are we clear now regarding with the example of equivalence relation?
Yes, sir.
All right. So once you're done with those examples or topics, then you may now proceed in answering seat break number 6. Okay, so in here, tell which of the following relations are equivalence relations. Okay, so we have 4 numbers. Okay, so again, when we see equivalence, it should be RST, reflexive, symmetric, and then transitive. All right, the next one here is set partition. So when we say set partition, so it is a partition under a certain set. Okay, like for example, we have here the X, as we could see that this one is your superset, okay, containing all of the elements 1, 2, 3, 4, 5, 6, 7, 8. And then we have here the partition of that set, which is in symbol S, wherein we have an elements or set inside a set, which is 1, 4, 5, 2, 6, 3, and then 7, 8. Then as you can see, this one came from this supersets. That is why this one is called a partition of a certain set or superset. Okay, so S is a partition of X, since if you're going to form the this one Cartesian product on each of those sets, so 1 1 1 4 1 5, 4 1 4 4 4 5 5 1 5 4 5 5. So you will get a classes 1 4 5 for this one, and then 2 6 for another say following order, and then we have 3, and then we have 7, and then 8. Okay, so what are those classes that I'm talking about? So later on I will show you guys what are those classes, but for now this one is composed of 4 classes, a total of 4 classes. So each class of course composed of students. So just imagine that one similar with a simple class or a normal class, where in this one we have student number 1, student number 4, and then student number 5. Okay, and so on and so forth. Right, so enough with that. So let me just show to you guys this one as a representation of the set partition using a diagram. So we have the 1 1 up to 8 8. So all of those are this one. Okay, 1 1 1 3 3 1, and so on and so forth. Okay, so for now I will leave the analysis part into you guys. So this one is not that important when it comes to classes. So yeah, this is just a representation of this set. Okay. All right, so let's now move on to the main topic, which is called the equivalence class. Okay. So let R be an equivalence relation on a set X. So the sets A defined in set partition are called equivalence classes of X given by the relation R. So as you can see right here, we have formed a total of 3 classes. So this one is one class, and then another class. So we have 3 classes under this set partition. Okay, so how did we come up with that one? So later on, I will give you guys more examples. So for now, in here we have a total of 3 classes. So 1 3 5 one class, 2 6 one class, 4 is another class. Okay, so let's have this simple example. So we have this relation. We have the AA, BB, and then CC. So as you can see, this is like one class. So A is related to A, or A is classmate with A, B is classmate with B, C is classmate with C. And as you can see, since if we're going to represent this one using a class, it will be in the form of set. So supposedly we have AA here, but this one is of course a set, so we only need a distinct element. So just retain here A. So this one is already one class, and this one is another class, and then another class, forming 3 equivalence classes. Right? So let's move on to the next example, which is the most complete example when it comes to equivalence classes. So the question here is, how many equivalence classes are there in the following relation? So we have this relation 1, 1, 1, 3, 1, 5 up to 5, 5. All right. So let us now. I hope that you guys can still follow, since I'm making it quite fast-paced discussion since we don't have enough time anymore. So can you guys still follow? Or just a little?
Just a
Medyo,
little,
sir.
sir.
All right. So what's one? Take attention. Pay attention. Okay, not take attention. Pay attention to this one, since this one is the most complete example when it comes to equivalence classes. So you can see right here, we have here relation. So the question here is, how many equivalence classes are there in the following relation? So the first thing that you need to do in here is list all of the distinct elements. Okay. So in other words, we have to form the superset from this relation. So as you can see, we have one. Oops. We have one. We also have two. We also have three. We also have four. We also have five. And then we have six. No. Okay, so 1 to 5 only. So basically, we have a total of 5 students, okay, or 5 distinct elements. So our goal here is we need to find how is 1 related to 2, how is 1 related to 3, etc., etc. So how are they related with each other? So in that case, once we've learned this one is related to this one is related to this one, we'll be able to know who are the classmates among those 5 students, and then forming a class, of course. Okay, so like for example this one, so 1 is the classmate of itself, and then 1 is again a classmate of 3. So we could say that 1 is equal to 3 elements or student, and then 1 is also related with 5. So we are like saying that 1 is a classmate of 3, 1 is also a classmate of 5, 3 is also a classmate of 1, 3 is also a classmate of 5, etc., etc. Okay, so they are classmate on a single class. So what else? So do we have 1, 4? Okay, so we don't have 1, 4. So this one is already forming one class. Okay, 1, 3, 5. So this is one class wherein we have 3 students, which is 1, 3, and then 5. All right, so let's now move on to the next one. We have 2. So 2 is related with 3, so they are classmates with each other. 2 is also related with 4, so they are classmates with each other. 2, 5. Do we have 2, 5? None. All right. So from here we have formed again another class which is composed of students 2, 3, and then 4. All right. So just keep on doing that one up to the last element. So 3 is related with 1, and 3 is related with 2, and 3 is related with 5. This one. Do we have 3, 4? Right, so we don't have. So here, this one is already, or again, forming another class. So we have 1, 2, 3, 5. 1, okay, so we'll just follow the arrangement. 3, 1, 2, and 5. All right, so for number 4, 4 is related to 2. And then 4 is related to no more. Okay, so this one is again another class. 4 and then 2. So it doesn't matter what is the arrangement. So it could be 2, 4, or 4, 2. So they're just the same, since in a set, arrangement doesn't matter or order doesn't matter. And for 5, 5 is related to 1. What else? 5 is related to 3. What else? No more. Okay, so this one is having a class of 5, 1, 3. Oops. All right, so there you go. So for now, of course, we have a total of 5 class: 1, 3, 5, 2, 3, 4, 3, 1, 2, 5, 4, 2, and then 5, 1, 3. And if you're going to take a look at this one, 1, 3, 5 and 5, 1, 3 are the same. Okay, so meaning, so those three are having a one class only. So since we are talking about set, then we could already eliminate the similar component or similar elements. So this one counts as one element only. I mean, one class only. Okay, so this is forming another class, and then another class, and then another class. So we have a total of 4 classes. All right. So did you guys understand this one? Equivalence classes?
Yes, sir.
All right. So how about the others?
Okay.
Yes, sir.
All right.
Yes, sir.
The things that you need to do here is list all of the distinct elements and then check how are they related to each other, and then check what are the similar elements or set that you're going to have. So if ever there is, then just remove uh, those similar set. Okay. All right. So we have another example here wherein let x is equal to 1 to 10 and define x is related to y if 3 divides x minus y. So you could only say that we are in relation if we have met this condition. So as you can see right here, determine the members of the equivalence classes of, so excuse me, so y is already given. Okay, so this is your x, and then this is your y, which is 1, 2, 3. Okay, so from there we could already compare the x and y on how are they related to each other using this condition. So we have, let's say, 10 minus 1 divided by 3 is equal to let's say a 0 remainder. Okay, so it's not even or it's not odd, so having a result of 0 remainder. So 10 minus 1 divided by 3 is 3. 7 minus 1 divided by 3 is 2. 4 divided by 1 divided by 3, 4 divided by 1. 4 minus 1 divided by 3 is 1. Okay, and then 1 minus 1 is 0 divided by 3 is again 0. Okay, so as long as you have a 0 remainder, then you're good to go. Okay, so from there we have formed all of the possible elements of this class. Okay, so we have 1, 4, 7, and 10. All right, so if you're going to do this one on the next set, or let's say relation, which is under the 2 elements of y. So you will get 2, 5, 8, and then for 3 you will get 3, 6, 9. So from there you will get a total of 3 classes or 3 sets of partition under set X. Alright. So did you guys get this one so far?
Medyo po.
Okay. So your goal here, for example, number 2 here is determine the members. So in here we've just determined the members that this one is x that is related to y. Okay, if we have a y of 1, and this one is the x if we have a y of 2, and these are the x if we have a y of 3. All right, so again I'll leave the analysis part to you guys once we're done with our discussion. So here's your seat work number 7. So determine whether the given relation is an equivalence relation on 1, 2, 3, 4, 5, and if the relation is an equivalence relation, list the equivalence classes. So in here you need to do a double validation. So first you have to identify whether this one is an equivalence relation. But if not, if they are equivalence relation, then you have to list all the equivalence classes. But if not, then you don't need to list the equivalence classes anymore. So yeah, that's it for this set of activity. And then the next one here is determine whether the given relation is an equivalence relation on 1, 2, 3, 4, 5. And if the relation is equivalence relation, list equivalence classes. So from here, you're going to have three step or three process. So in here, two process only because the ordered pair is already given. But in here, you need to list the ordered pair first before you can verify whether this one is equivalence relation. And then if ever it is an equivalence relation, then list all of the equivalence classes. Right, so 4 numbers also. And then for the last one, so list the members of the equivalence relations on 1, 2, 3, 4. So also find the equivalence classes of 1, 2, 3, and 4. Okay, so you need to find the members and then the equivalence classes of those given expression. Okay? So A to E. So I'll give you guys 1 minute to take a look on this secret. And let me know if you have clarification or question. All right, so how was it? Is there a part that you guys are confused or none? All right, so we now only have 10 minutes. Anyway, so if you guys have a question or clarification, so feel free to ask me anytime on my Canvas account or Facebook account. All right, so yeah, so I'll leave this one on to you guys once we're done with our discussion. Okay, so just analyze this one later on. All right, so the next one here is matrices of relations. So is there anyone here who's familiar with matrix? All right, so I guess none since no one's speaking. Well, a matrix is a convenient way to represent a relation R from X to Y used by computer to analyze a relation. So this one is super similar with X coordinate and then Y coordinates or the graph, X and Y graph. But in here, we have to fulfill the missing say coordinates. If they are not in relation with each other, then you should write there 0. And if that coordinate is in relation with each other, then just put there 1. So that's the only difference between a matrix and then a graph, okay, X and Y graph. All right, so just take note on this one. So row is representing the X element, and then Y is representing the column element. Column is representing the Y elements. All right. So here's one example. So we have here the relation 1B, 1B, 2C3, C3, B4A. And then we have here the coordinates of your X, 1, 2, 3, 4, wherein we have this order 1, 2, 3, 4. And then we have A, B, C, D for the coordinates Y. Okay. And then just plot, okay, or just fulfill everything from here. So we have an ordered pair 1B wherein they are in relation with each other. So just put there 1. And then we have 1B. So just make this one 1. Then we have 2C. We have 3C. We have 3B. And then we have 4A. Okay. And then the rest, once you're done in filling up the, say, related ordered pair, just put there 0 on the other coordinates. All right. So did you guys get this one so far?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Very good. So let's have another example. So in here we have the same. Okay, oops, is it the same? Yeah, we have the same ordered relations, but just a different orderings. So before we have 1, 2, 3, 4, and then A, B, C, D. But right now we have 2, 3, 4, 1, and then B, B, A, C. So you have to be wary on that one. Okay. So just look for 1B. So 1B. So make that one 1. 1B, make that one 1. 2C, make that one 1. And then 3C, make that one 1. And then 3B, make that one 1. And then 4A. Okay. So the same concept. So just fill up everything by 0 once you're done in filling up the related uh, elements or coordinates. Okay, so note the matrix of a relation from X to Y is dependent on the orderings of X and Y. Okay, so always take a look at the orderings of your X and Y. All right, so did you guys get this one?
Yes, sir.
How about the others?
Yes, sir.
Gets.
Yes, sir.
Okay, so let's have another example. So in here, write the matrix of the relation R from 2, 3, 4 to 5, 6, 7, 8 relative to the orderings 2, 3, 4, and then 5, 6, 7, 8. So as you can see, our orderings are still the same. So we have the 2, 3, 4, and then 5, 6, 7, 8. So no problem. But in here, we have a condition wherein define X is related to Y if X divides Y. So as you can see right here, your Y here is 5, 6, 7, 8. So just take a look on this one. 5, 6, 7, 8 divided by these rows. Okay, 2, 3, and then 4. So 5 divided by 2, so 0 since they are not related with each other. And then 6 divided by 2, so yes, so just make that one 1 since you can divide 6 by 2. 7 divided by 2 is no. 8 divided by 2 is yes, so just make that one 1. 6 divided by 3 is a yes. And then 8 divided by 4 is a yes. And then the rest are already 0. Okay, since they wasn't able to form a relation with those two coordinates. So, understood or no? Did you guys
Yes po,
get?
sir.
All right. So, I'm afraid we're going to have a part 4. Okay, so kasi meron pa tayong next na topic mamaya. Anyway, so let's have this example number 4. So write the matrix of the relation AA, BBC, CD, BC, and then CB. So as you can see, just plot everything on this orderings. We have ABCD and then ABCD. Okay. So BB, BC, CB, and then CC, and then DD. Right? And yeah, so this one is actually like representing a reflexive matrix and then at the same time symmetric matrix. All right, so you have here your seat break number 8. So find the matrix of the relation R from X to Y relative to the given orderings. So just be wary when it comes to writing the orderings. So we have this list of relations, and then here's their orderings. 1, 2, 3, alpha, beta, sigma, and then I don't know this one. And so on and so forth. So 3 numbers for this one. And for number 4 and 5, so find the matrix of the relation R on X relative to the given ordering. Okay. So yeah, this one is a lot more easier since we only have one ordinings. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the relation is already given, but in here, the relation is not yet given. So you have to verify what are those relations or set order. Okay, and then for the last one, write the relation R given by the matrix as a set of ordered pairs. So from here, it was in a matrix form. So it is asking you to form or to give you or to have a result of ordered pair like this one. Okay, yeah, 1, 2, 2, 3, 3, 4, 4, 5. All right, so that's it for your work number 8. So are we clear so far for your secret number 8?
Yes, sir.
All right, how about the others?
Clear, sir.
Okay, so we don't have enough time anymore. So sorry, we wasn't able to finish this module for 3 Zoom meeting only. So I will stop our meeting now and then just wait for the part 4. So anyway, your part 4 won't be having a long discussion since you only have 7 slides left. Okay, so maybe 10, more or less 10 minutes. Right? So see you guys on part 4. Right? So overtime.